Okay, can you see my screen?
Yep.
Amazing. Okay. Awesome. Hi, everyone. It's really great to see all your little faces on that side of the camera. Wish I could be there. It sounds like a really amazing event. So really grateful to be able to share some of the work that PKIC does, and hopefully it's useful to you in some way, or you learned something new today. So my name is Nina Nichols. I'm calling from beautiful Lekwungen territory of the Songhees, Esquimalt, and Wasanich nations. And yeah, right now all the camas are blooming, which is just which is super stunning, and a great reminder of one of the important traditional food sources for many First Nations on the South Island. So it's really lovely to see the camas fields that are continuing to thrive today. So I'm going to be presenting on climate data and projections in BC, so a bit zoomed in from Sylvie's presentation. So a little background on the Pacific Climate Impacts Consortium, or PKIC. We are a regional climate service provider, and that just means that we conduct science on climate change and climate variability. And a lot of our staff focuses on climate research, modeling, and downscaling climate data. So downscaling is translating that coarse resolution of global climate models that Sylvie mentioned into smaller spatial scales, so down to a 10-kilometer by 6-kilometer grid. And that's done using statistical relationships between models and observational data. And it allows climate data to be more easily used by regional and local decision makers. So it's pretty amazing. You can click anywhere in BC and get climate projections for a 10 by 6-kilometer grid. And at PKIC, I work under the user engagement team. So that's supporting organizations and communities to apply climate data in their work. So if there's any work that you're looking to use climate data, please do feel free to reach out to me. And so when I'm talking about climate data, I'm talking about projections of average future climate conditions for a variety of temperature and precipitation-based variables. And I'm going to dive into those throughout the presentation. And I do want to note that climate data alone doesn't provide clear answers. So it provides information around the degrees of change and the long-term trends, but it really needs to be embedded into a planning process that includes your specific contextual information to best support planning and action. And it is only one way of knowing. So it's important that it be considered alongside other forms of knowledge, like Indigenous knowledge or local and land-based monitoring efforts, because really the more forms of knowledge we bring forward, the better and clearer the picture of the future we paint can be. So in talking about climate change, it's important to distinguish between weather and climate. So looking at the image here, weather is what happens fairly immediately between days and months. So maybe a couple of days of rain or a heat wave that lasts a week. And then in that intermediate time frame from months to decades is where we see natural climate variability. So this is variability in the natural climate caused by forcings that are non-human related. So for example, most of us have heard of El Nino events, which are caused by fluctuations in temperature between the ocean and atmosphere, and they're quite significant here in BC. So right now, some scientists are predicting that we will soon be entering El Nino from La Nina. This is a bit concerning because it means we can expect warmer temperatures than we have experienced for the last couple of years. And then on the decadal to century cycle, that's where we measure climate change. So generally, at least 30 years of data is needed to determine a climate trend. And it's where we see things like global warming or changes in sea level rise, so on and so forth. So climate change is both the changes in average conditions over long periods of time, so those 30-year averages, like I mentioned, and it's also the change in climate-related extreme events with different intensity and frequency. And both of these types of changes are linked. So a location may have overall decreasing precipitation throughout the year, but more rain may fall over shorter time periods or more intense rain, which can cause more damage. So here are a quick graphic. So what does it mean that we're raising the average temperature? So in thinking about increasing that long-term average, it also has an impact on those extreme ends of that range. So as the average shifts, so do the high and low ends of that projected range. So if our average temperature is getting warmer, those hotter temperatures are going to become much more likely in our future climate. And then on the other end of that spectrum, we see a loss in cold in many projections due to that shifting curve. And so where does all this information come from? Well, scientists have developed complex climate models to represent our climate. So these models are mathematical representations of our Earth systems, and they are extensively tested against observational data. And to account for uncertainty in models, climate modelers use ensembles of multiple different global climate models to describe the range of possibility. So here we are looking at projections for very hot days in BC. And in red is each individual global model from a different research group around the world. And the black line represents that ensemble mean. But you'll notice there's also that dotted line on the top and the bottom. So that shows the 90th and the 10th percentile. And this is the way that climate data is generally displayed, showing both the range and the mean, or sometimes the median. And this is really important because that range is really important to consider that possibility of what might happen. So when you're looking at climate data, yeah, just important to consider the range as well as the mean. Okay, so now we are looking at average temperature in BC compared to a 1970 to 2000 baseline. And this is similar to what Sylvie showed you, so I'll be kind of quick. But the gray shading here, box, represents that modeled historic average climate in BC. So what the models said the climate would look like. And that black line with all the ups and downs is what was actually observed. And you'll see there's a lot of natural climate variability from year to year. Some years are warmer and some years are colder. But we can see that the range of climate models in gray actually does a pretty good job of capturing that observed climate variability. So all to say that the models are doing a pretty good job. And now moving to this future portion of the graph. So everything we know about the future is generally uncertain, right? We can't predict a lot of things, and climate models are no different because we can't predict social, technological, and political choices of the future, which are going to impact how much greenhouse gases we emit and ultimately how much the climate will change. So scientists use different emission scenarios to model the range of possible futures. So here in recent modeling, these are the emission scenarios that have been used. They're called shared socioeconomic pathways, or SSPs. And they include 5 pathways that illustrate different ways in which global societies may develop. And each includes the greenhouse gas emissions along with a certain level of warming. So just to note a few, this is SSP5, that's a high emissions scenario. SSP1 is that low emission scenario. So assuming that we transition away from a fossil fuel based economy, that there's a low consumption, low population growth, so on and so forth. And then if we bring those back to the graph, so this red one is SSP5, it's that high emissions scenario. And then in the yellow here is SSP2, so that's that middle of the road scenario. And SSP1 is that low emissions scenario. This SSP1 in blue most closely aligns with the goals of the Paris Climate Agreement. So that's constraining that warming to 1.5 to 2 degrees that Sylvie mentioned. But it is worth noting that this is a really ambitious goal. And according to the IPCC, considering current global emissions reductions commitments, we're actually on track to exceed this globally. So that's just something to keep in mind when you're choosing an emissions scenario to look at climate data with. And another thing to note is that in all of these scenarios, the future is warmer than the past, and that range of potential future conditions is also a lot larger. So really, we are not returning to the climate of the past. We are continuously entering a warmer climate as long as we continue to emit greenhouse gases. So even if we hit net zero and eventually the climate stabilized, we would be stabilizing in a warmer climate. And you'll note that in the middle of the century, so around the 2050s there, a lot of these scenarios are closer together. And then as we move out to the end of the century, they're much more distinguished from one another. In particular, if we look at that high emission scenario and we look at the coldest possible years of that future, or the lowest projections there, you'll note that they're higher than even the warmest temperatures of the past. So this is a very different climate and a very different place. And even in that low emissions future, it is still warmer than the past and is still going to require adaptation. So considering these end of century projections is really useful for long-term planning and assessment of potential risks. Okay, so I'm going to shift a bit to talking about what does that look like in BC. So in BC, there are a couple of trends that we see consistently across the province. In general, we can expect warmer winters, hotter, drier summers, wetter winters and shoulder seasons, and an increase in frequency and severity of precipitation and storm events. Remembering variability, so these changes won't always happen consistently over time or across regions, as natural, seasonal, and yearly variations will still occur. So I'm going to pull up a couple of examples that illustrate these trends from across the province. And I thought I would start where you all are in Lytton, BC. So this variable is days with temperature above 30 degrees. So it's a variable that illustrates that trend of an increasing heat, more hot days, and a greater range of potential hot days. So if we look at Lytton, we can see historically, so the 1971 to 2000 average was 21 days above 30 degrees. And as we move farther into the future, that number is increasing. So if we follow a middle emission scenario, we see that it increases to about 40 days on average by the middle of the century. And then at the end of the century, 44 days. And under a high emission scenario, you can see that increase is quite substantial. So it is a very substantial shift. And so it's really important, if we know this information, what can we do now to better prepare for this increase in heat? Now moving to precipitation. So again, this is a common trend we see in BC. And this table comes from the Metro Vancouver projections report that PCIC developed. So if we look at precipitation, we see a modest annual increase by the end of the century, 11%. But most of the increased rain will fall in already wet months, with fall and winter seeing the largest increase, especially that fall season is generally where most of the increase is happening. And then you'll also notice that in the summers in this region, they're projected to get significantly drier and longer. So this type of trend can contribute to more frequent flooding, as longer drought dries the soil and reduces its capacity to accept water. So drought followed by extreme rain or even modest rain can lead to more overland flooding. And less rain in those hotter summer months might cause drier conditions, which can lead to things like wildfires. And this trend is consistent across the province, except in the Northeast, where there's not a projected significant decrease in summer precipitation. Okay, and one more. So now we are looking at variables that highlight that loss of cold in those winter months. And we're going to look at the terrace region, looking at a variable called ice days. So ice days are days when the daytime high, or just the temperature, I guess, stays below 0 degrees Celsius. So in the past, we see there were 75 days on average of ice days. And then as we move into the end of the century under a high emission scenario, that goes down to about 28 ice days. So from around 2.5 months to less than a month of ice days. So this can affect ecosystems, agriculture, transportation, all sorts of things. And additionally, because of those higher winter temperatures, terrace and many regions can expect warmer winter seasons, which will cause more precipitation to fall as rain rather than snow. By the 2050s in the terrace region, we can expect snowfall to decrease by 50% and then 66% by the end of the century. So again, a really big shift, and that's where those adaptation measures can come in to support communities to prepare for these changes that are very likely to come. So now I'm going to shift again to talking about where can you find this kind of data. As Sylvie mentioned, climatedata.ca is a really great place to start. A lot of available information. You can look at a map view, type in a location, and just automatically get a bunch of projections for whatever variable or location you're interested in. PCIC also has some tools that can be useful. One is our Plan to Adapt tool, which is a really great tool for beginners and a really great place to get comfortable with climate projections. You can get these kind of automatic summaries for a location you search. It doesn't use those 10 by 6 kilometer grids, but you can choose from regional districts or health authorities, forestry regions, or eco provinces. So a little bit different than climatedata.ca in that sense. And then there's two tools that I wanted to highlight for building design. So these two tools exist to assist in designing a climate-ready built environment. And that's because the National Building Code of Canada recognized that buildings need to be designed to withstand climate change, but it doesn't currently prescribe how building designers should do that. So PKIC has two tools to help designers do just that. The first I want to talk about are weather files. Weather files are very important components of building performance simulations or energy modeling and help with the design of heating, cooling, and HVAC systems. The weather files, primarily in use by energy modelers in Canada, have the acronym CWEC, but these files are based on historical climate information. So historical files will generally underestimate cooling demands, overestimate heating demands, and that's because our climate has already changed and will continue to change. So what PKIC has done is adjusted these historical CWEC files to take future climate into account using a high emission scenario and making them available for 3 30-year time periods. So the 2020s, 2050s, and 2080s. And these files are plug and play. So all a designer has to do is access these files on our websites and use them in the exact same way that they would use historical weather files. And they are free to access on our site. You don't need to log in or anything like that. So if you are involved in any building design process, this is for you. And the very last tool I want to make you aware of is the Design Value Explorer, which are for those who work with building codes. So the National Building Code of Canada has a very large table in it called Table C2, and it has a number of prescribed climate design values for various locations across Canada. These design variables help with things like structural loading concerns for a building, but the values provided in this table of the code are currently based, again, on historical climate data. So the Design Value Explorer is a heavily researched and credible tool that provides future projected design values for those same climate variables that are required in the building code. And they are available for different levels of future global warming, which you can see in this table here. My animations are off. And one thing that I will note about the Design Value Explorer, I am no expert in it, but there are some people from PKIC that are doing a webinar on all to know how to use this Design Value Explorer. So again, if you're interested, here's some information. You can reach out or find it on the website. And all of this to say, climate data can support planning for the future by providing information and a sense of the degree of change we can expect. So here's an example of an adaptation plan. Really, climate data is only used at that start, and then from there, discussing impacts on the land, impacts on the community, and then discussing collaboratively what are some adaptation actions that can be taken. So climate data is a small part of the process as a whole, but it does play an important contribution. Thank you very much for listening, and please feel free to reach out if you have any questions.
The camera's over here.
Can you hear me now?
Yes.
All right. All kidding aside, told you the Earth's air, land, and water is heating up. There's no going back to yesterday. So why would you build Lytton for yesterday's weather? Why are we having a building symposium with the future in mind? We have an opportunity to design homes and supporting systems and infrastructure to handle what everybody's talking about. What an incredible opportunity. Don't get me wrong when I say, don't tell that to the people of Lytton. Some of us lost our home, built in 1973, never designed for the heat, never designed for the cold or the fire exposure we have today. I'm going to build my home for the next 100 years. I'm going to go out here and I'm going to look at the tables and I'm going to pick the products and the systems that I need. And just letting you guys know what's coming. Now, even if we throw the trillions of dollars at harm reduction, that means quit releasing species into the air. Even if you throw the trillions of dollars of getting it down, it's called lag time and inertia. It takes time to stop us. We committed to 1.5. We're going to stop the global temperature at 1.5. Did you see they said, oh, and here's forecasting at 2.4? Kanaka Bars already forecasted a 6-degree change at Kanaka. Right? Prepare. What do you say? What's that old saying? Hope, prepare for the worst, hope for the best. We are facing a global existential crisis. Climate change is real, and we're living those effects now. And as we segue into the next presentation, and I'm so sorry. And what happens is, Nina, there's no, and Amanda and Sylvie, if you guys want to listen in, we have 2 speakers featuring next, because what climate change is doing is impacting our natural and built systems. How do we know this? Because your next speakers are going to tell you what happens when it gets too hot and get too cold, in theory. So step outside. Remember, everybody, this is being recorded. Paul doesn't have a presentation, but Technical Safety BC does. We're not gonna abandon you guys. You get to hear now. Why would the recovery manager, Patrick? I owe you one. Didn't I say ask him what time you can start rebuilding? Is that why it was? Anyway, I digress. We still have, and we will delay. So we want Paul and Technical Safety BC to do their presentations. Go eat. It's being recorded. What you've heard for those, if you have questions, comments, or concerns, this is being recorded so you can locate the people afterwards. If not, ask the mayor or a chief. I'm retired, chief, remember?